The University of North Carolina at Chapel Hill is developing a telepresence video wall system for enabling informal conversations between remote coworkers. In this project, 2 video walls have been constructed at UNC. Each video wall consists of 4 large screen displays and a teleconference audio system. Eye contact is facilitated by switching between 2 sets of cameras as people approach the displays to speak with one another. During the switching process, foreground image segmentation is applied on the image sequence of right-ahead personal cameras. Distracting duplicate image artifacts are removed in the image sequence of panoramic cameras. In this way, the small artifact segmentation of foreground users could provide high-quality, one-on-one conversations with both accurate eye contact and a nice panorama view. The UNC team has implemented an image segmentation algorithm that leverages the Microsoft Kinect depth sensor to produce a segmentation that addresses foreground segmentation in a general dynamic environment. Foreground segmentation in a dynamic environment depends a lot on real-time geometry and information of the whole scene. Previous segmentation algorithms that combine background subtraction and stereo-based image segmentation work well on simple environments where background movement is small and the foreground region is salient. However, it is error-prone and easy to fail when background objects move a lot or foreground people's clothes have similar colors as the background. Microsoft Kinect cameras have an IR projector, IR camera, and color camera. The IR projector emits a light pattern into the scene. The Kinect calculates depth by comparing the projected light pattern seen by the IR camera with a known reference pattern. The resulting depth map is then transformed to align with the color image. This produces a color image with additional depth value at each pixel. The segmentation algorithm is composed of 4 parts: floor subtraction, connected component labeling, threshold segmentation, and color refinement. First, the floor region is subtracted from the background image using the depth map. The Kinect is carefully calibrated to find its position and orientation with respect to the floor of the office. This geometric relationship is used to project each 2D depth map pixel as a point in 3D space. The floor of the office is defined as a plane in 3D space. Each 3D point that falls below this plane is back projected onto the 2D foreground image. The resulting set of back projected pixels are used to subtract pixels belonging to the floor. Next, a connected component labeling algorithm is applied on the floor subtracted depth map to get segments of different objects. In this step, pixels are grouped into components by examining the difference between the depth values at neighboring pixels. If the difference between 2 neighboring depth map pixels is smaller than a given threshold, they are assigned to the same component. The next step is threshold segmentation. The components are then labeled as belonging to the foreground or background. Each component is represented by 1 or more pixels. Each component is assigned to the foreground if the average depth value of these pixels is greater than a given threshold. Here, the distance is set to 1.5 meters to facilitate foreground segmentation at a comfortable speaking distance from the display. The final step is to perform color refinement. Human hair absorbs IR light. In practice, the team has observed that the Kinect's projected IR light is readily absorbed by black hair. The resulting IR signal is weak, and the Kinect often fails to produce depth values. In this refinement step, the color image is divided into superpixels based on an over-segmentation algorithm. The resulting superpixels are then connected with the previous foreground components to include black hair. The Kinect-based foreground segmentation method successfully separates foreground regions from complex, dynamic backgrounds, enabling 2 people to maintain an uninterrupted one-to-one conversation without the environmental setting constraints. The team is currently working on multiple Kinect collaboration and to integrate this method into a larger video wall. In addition to improving image synthesis by foreground segmentation, the team has also constructed a novel view rendering system by using multiple Kinects. Because of the difficulty of achieving real-time, high-quality 3D scene models, one of the challenges in a telepresence system is real-time novel view generation. The Kinect gives the chance to overcome this by producing relatively accurate 3D data of a scene. After carefully calibrating multiple Kinects, the team successfully merged 3D data from 2 Kinects using both perspective view and orthogonal view rendering on a television wall using the merged 3D model. Since the 3D data provided by the Kinect contains a small amount of noise, and the point cloud of the background is sparser than the foreground, the final rendering result is less accurate. The team is currently working on 3D data filtering and refinement to get better 3D reconstruction using multiple Connect units.